Do you hear me? Yeah,
Yes,
okay.
yes, I
So
do.
I will be the chair, at least Layla told me.
Yes, I do. I do hear you, which is
Okay, are we all now?
no, not short of a miracle.
I think we are. So let's wait another minute.
Mhm. No problem. No problem.
Okay, so welcome to the afternoon session on this workshop of Abelian geometry and related topics. And there will be a talk by Pierre Lochak in Paris and somewhere else in the world. And he will talk on the grothendieck-teichmu group and past and present. Okay, we are looking forward to hear you.
Okay, so thank you very much for giving me the opportunity to talk about this topic, which I think the theory of the grothendieck-teichmu, which you can call a theory, suffered from a lack of maybe a lack of background, really, because as I'll try to explain, uh, there are at least two brands, two variants of the theory. One of them being pro-algebraic, the other one being pro-finite, and the pro-finite theory, which is much more in the line of Grothendieck-esquisse program, which is what it is. I mean, this isn't not an argument of authority, but this is a fact, and it has been largely overshadowed by the other variant, which is pro-algebraic and in fact pro-unipotent, and I'll try to explain why. But first, I'd like to tell you about more specific. I mean, I'll put things maybe a little upside down in the sense that I'll try to start with rather specific results and specific things in general, and then maybe move in the second half of the talk. I think I'll give you a larger. I'll try to brush a larger uh, context for the theory, because I feel really keenly that it's difficult to understand what's going on if not against a rather large historical background. So let me start first with more specific kind of things. So first, what are the objects we're going to talk about? So let me. I know this is may not be the acme of of technology, but I'm using a blackboard all the same. So you have a surface S, which is as usual genus G and N mark point. Oh, maybe you don't see it. I'll try to write really big. So S is SGN, and then attached to that surface you have a certain number of uh, of objects. So one of them is the moduli. So it's supposed to be hyperbolic. So 2g minus 2 plus n, which is minus the Euler characteristic, is positive. And so you have a certain number of objects. So you have the moduli stack of S. So always that's one of the miracles of the theory. You have several viewpoints. One is topological, then you have the hyperbolic viewpoint, then you have the complex theoretic viewpoint, you have the geometrical algebraic viewpoint, and you have the arithmetic viewpoint. So the thing is, one of the miracles is that they all go together, but the words are somewhat different. So for instance, M of S is the moduli stack of curves. So it's a Deligne-Mumford one stack for people in algebraic geometry. It's also an orbifold for if you're a topologist or if you work more in complex geometry. Then you have Teichmüller space. So Teichmüller space is only an analytic object, so it does not exist, quote unquote, in terms of algebraic geometry. And then you have the mapping class group, also known as Teichmu modular group. So T of S is so it's technically it's Galois unramified in the orbifold sense, or it's Galois unramified in terms of stacks with over M with Galois group gamma of S. Sometimes there's a minor issue is whether you permute points or not. So sometimes you write this with square brackets if you can permute points. Well, okay, I will not make it always quite precise whether points can be permuted or not. This is really a minor issue. And then the thing I'm going to talk about more are these complexes. So the theory has been one of the goal of maybe today, but it's actually goes back to like 25 years ago, is to replace the phrase, or not replace, or say, give a variant of the phrase group theoretic, which will be complex theoretic. So you go from a theory which is based on group theory to a theory which is much more based on geometry, So in some sense, I mean, in a very definite sense, we want to start the profinite geometry of surfaces. So mark the words. I mean, it's not profinite groups. It's profinite. It's the geometry or profinite geometry of surfaces. When I say start, again, it started like 25 years ago, and it has been largely ignored for several reasons. Some of them I'm responsible for, and others are more historical kind. Okay, so this is the, and I didn't tell you who these people are. So C of S, for now, let me just define C of S. So C of S is very simple. So so the dimension of the moduli space of S, I call D of S, and is 3G minus 3 plus 10. And so the dimension as a series, a complex orbifold. And that C of S is a simplicial complex. Simplicial complex of dimension D of S minus 1. So D of S is, you call it the modular dimension of the surface, because it's the dimension of the moduli space attached to the surface. And, well, let's say, let me draw a genus 3 surface, G equals 3 and equal 0. And probably most of you have seen it already. So a simplex of, a K simplex of CK of S. So the K Gaussian of S is made of simple, non-intersecting simple curves. And K plus 1 non-intersecting simple curve. So a vertex is exactly a simple curve. So as usual in mathematics, there are very few things which have happened recently without Jean-Pierre Serre being involved at some point. And these things were introduced by William Harvey around 1970 after conversation with Serre, because they are the C of S, which are very much used to, they're called curve complexes, They're very much used by topologists as a kind of quote unquote coarse graining of Teichmuller space. And they are the analog of, say, buildings for symmetric spaces. And there is an ongoing analogy between Teichmuller spaces and symmetric spaces. And this is, in some sense, the analog of what Borel and Serre did in the 50s for the Bordification of symmetric spaces. Well, then in the 1980s, well, I'm already doing a little bit of history. In the 1980s, it was very important to the ller on the one side of the Iron Curtain and Ivanov on the other side determined what the homotopy type of this visual complex. It's equivalent to a bouquet of spheres, and it was very important. It led to the famous Madsen-Weiss theorem, which uses it in a crucial way. So this is pure topology, but for instance, determining the homotopy type of C of S was a key to unlock several things in algebraic topology in the 1980s, 90s. Okay, now CP of S and C star of S, hopefully we'll have time to meet them later. So what's happening is, why first be interested in these complexes? Well, most of the theory, starting with Grothendieck himself, has to do with gamma of S. That is the mapping class group, the Teichmuller group of S. And C of S is, how are they related? So one way they're related in several ways. Suppose you have an automorphism of this, then when will it give you an automorphism of C of S? Well, if and only if it maps a simple curve to a simple curve, or it maps a twist to a twist, which is the same. Now, thanks to a result that's very recent by Mochizuki and several people. Oh no, sorry. This is always true. In the discrete case, in the discrete setting, it's always true that all automorphisms are this way. Alt gamma of S equals alt star gamma of S for all S. In the discrete setting, this is the discrete setting, and this is because twists have a purely group theoretic characterization in the discrete setting, which is not available in the completed setting, which we will meet hopefully very soon. So you have this, but you have something which is better than this, which I just say. By the way, maybe I should say that I'm just going to give a very streamlined summary of many papers, and the two last papers are two papers I published in the St. Petersburg journal. They're quite recent, although they're talking about things which some of them were known or I've known for decades, literally, and so you can find them on my webpage. Well, of course, I encourage you to read at least part of them, because what I'm saying is just a very crude sketch of it, a sketch of a small part of it. So the point is, again, that you have this. So if you want to study the automorphism of the mapping class group, then you can just as well study the automorphism of the curve complex. But there is more than this. It is also true that if, okay, then let's, so I denote by lambda which is a barbaric way of it's barbaric for level. It's not Greek, but it's gamma lambda is any finite index subgroup of gamma. So by a result of Nikolov-Segal, which is a very also classical result, the open subgroups of gamma, which is finitely generated, are exactly the finite index subgroups, because any finite index subgroup is open. That's a very famous result by, again, Nikolov and Segal. So in fact, you don't need to consider gamma itself, but much of the theory will be sort of virtual in the sense that it will apply to any finite index subgroup or any cover of the spaces we encounter. So this is very important. I mean, this very important. This is, yeah, I mean, this is an advantage of a serious advantage of complexes over groups, that in any case, you can, in that way, handle all the finite index subgroup of gamma and not only gamma itself. So now, the first result, so all these things are, in fact, rigid. And the rigidity, the first result by two ladies, ller and Grossman, 1981, they prove that Bn equals C mod 2. So Bn is the uncolored, I mean the full braid group on n strands. So Bn is the full braid group on n strands. So it would correspond essentially to S being of genus 0 and also to points being possibly permuted. So they showed that the outer automorphism group, I mean, so divided by the inner automorphisms, is Z mod 2. Okay, Z mod 2, at this point it sounds like a bit snobbish and not very useful to identify with Gauer of the complex over I mean, Gauer of C over R, but it is actually what it is. And later it will appear as more interesting. So this was generalized. So everything I'm saying are really petty theorems and results, and they result from the 1980s and 1990s, and they're not easy. So this is generalized by like this. Like this for, I don't know, for, let's say D of S bigger than 1. So for the modular dimension, at least 2. Okay. So now the analog of this for the curve complexes, there is an analog, and the analog was proved by Ivanov, again, Nikolai Ivanov, and who showed that, so maybe I erase this, and Ivanov, so there are many Ivanov, of course, so this one is Nikolai, I think it's an I don't remember the initial, and this is, and this, you want to, this was supplemented, say, by Kochmas and Luo, and the net result is that the outer automorphism group of C of S is also Z mod 2. Because, I mean, here you have to explain what is the outer automorphism group. So the outer automorphism group by definition is, and it will always be the case with variance and for completions and so on. The outer automorphism group is just the automorphism group divided by gamma of S. So this, by definition, this is out E of S divided by gamma. So this is not exactly what you would call outer, but because it's not a group. But and also what you call an automorphism here, an automorphism is an automorphism of a simplicial complex. So when in the discrete setting, you've no serious difference between a simplicial complex and a simplicial set, for instance. They're basically the same, and automorphism is an automorphism of the simplicial set, of the underlying simplicial set, if you want. So it maps the K-skeleton to, or I mean, maps vertices to themselves and edges to themselves, and the K-skeleton to itself, and it's compatible with degeneracies and face operators. So this is well, the only reasonable definition of an automorphism that you can have. Now, another thing is that, in fact, you don't need to deal with the whole complexes. You can deal with graphs, and then and later you'll deal with prographs. So why is it so? So the first result, which is hardly a result because it's completely obvious, is that alt of C of S is nothing but alt of C1 of S. So it's the one skeleton. If you map correctly the vertices and the edges, then you're done. Why? Because what is it's called a flag complex. That is, any clique is a simplex, and that's is a simplex. Yeah, any in C of S, namely if it's simply because if you have simple closed curves and they are mutually non-intersecting, then all of them are non-intersecting, and so they form a simplex. So what you have to simply check is that you get an automorphism of the one skeleton, that is vertices and edges. So and this is a graph, of course. Maybe so. I'll tell you what CP of S. I won't tell you. CP of S is a two-dimensional complex. C star of S, which is something C star of S is really not so standard. I mean, I introduced it because maybe you'll see, or you won't see, or you would see in the papers why it's interesting. So this is a graph. So I won't tell you what this is. Although it's very well known, it's where you have the pentagon, and I'll tell you just what the graph is. There's dp1 of S. So the vertices, the set of vertices of these two are the same. Vertices of dp equal vertices of C star, and they're simply what we call the Pant's decomposition. Let's say the maximal multicurves. So this is so these are B of S non-intersecting simple curves. So you call it Pant's decomposition, you call it maximal multicurve, you call it the way you want. So it divides the surface into what, if you want to avoid the word Pant, you just say trinions, like Mochizuki. Mochizuki called them trinion. It's a nice word. So it's copies of P1 minus 3 points, or no, not P1 minus 3 points. copy of this. Okay, it divides your surface into trinions. So what's the difference? The difference is in the edges. So you have an edge between V1 and V2. So you have two Pence decompositions. If you have two Pence decomposition, you have an edge here. If okay, first first they have to agree on a surface of okay, so you have ds curves. So these two things have ds minus 1 curves in common. So so these two decompositions have ds minus 1 curves in common, which means actually they differ only on a surface of modular dimension 1, which is either a sphere minus 4 holes or points, or a torus. The torus with one hole. I mean, if you want an elliptic curve, and they here. So here, in this case, for C star, they're just any on the so they have a subsurface T with a dimension T equals 1, which is where everything happens, or which is either or this. And in the case of C star, they're just there's one curve here and one curve here, and they are just arbitrary. In the case of the Pence graph, so let's call it the Pence graph, then they're supposed to have minimal intersections, which is which I'm drawing like this. So they have here they have only one intersection point. Here they have two intersection point and algebraic intersection 0, because the signs are opposite. So maybe I should have said that, of course, everything is up to isotropy. And actually, if you would fix any metric of negative curvature, say curvature -1, to make it simple, then you can use geodesics all alone, because there's only one geodesic in each homotopy class. Okay. So this is classical, this is less classical, but it's easy to see that it's actually the one skeleton of the dual. So C star F is the one skeleton of the dual of C of S. It's very easy to, I mean, just you think about it, and that's what it is. So and I always take D of S larger than 1. For D of S equals 1, you have to make things slightly different, but it's not very different. I mean, you have to be careful. So then you have many quite a few important results, which I'm not telling you too much about, because it's too long. So for instance, you have the fact that you can prove what can you prove? Say you can prove things like that. So the astonishing thing is that even in this discrete setting, again, the discrete setting is supposed to be sort of understood, and you can still prove rather new things. So, for instance, you can prove that alt star S is nothing but alt C of S, that alt CP of S is included in alt CFS, and all in all, you simply prove that alt star S equals to alt, no, out, let's call it out, CP of S, it's also out, so they're all equal. I insist that these are non-trivial results. For instance, you recover a result of Margalit, which is in Duke in, I don't know when, well, it's listed in the reference list, which tells you that out CPFS, that CPFS is rigid. And also it tells you that, well, several things. And there is also another thing, which I guess I'm not going to talk about, which is reconstruction. Reconstruction is a very nice thing, which is also new even in the discrete setting. And reconstruction tells you that, in fact, well, let me say it in word. Suppose you have in what is reconstruction about? It's recognizing graph theoretically against this new phrase, or maybe not so new phrase, has to be, I'm not saying it will replace group theoretical, but it is in some sense an alternative. So the reconstruction principle is that you can recognize the complexes attached to a subsurface. So what is a subsurface? For me, a subsurface is if you take a simplex of C of S, and then you take sigma cut along that simplex. This is a subsurface. Okay, all subsurfaces are like that. So you take any simplex, which is just a finite set of non-intersecting closed curves. You cut your surface along these curves, and that gives you what I call a subsurface. So so the recognition, and it's really important because it works also in the completed case to some extent, but I'm not going, I mean, I can't really explain. It says that if you have a subgraph, if you have a subgraph of C star of S, say you have a subgraph of C star of S, which is abstractly isomorphic to C star of, so you have C, a subgraph of this, and C is abstractly isomorphic to C star of sigma for some surface sigma, and which is maximal with that property. That's very important. Then it is and maximal. Then C is nothing but C star of S sigma for some sigma. In other words, you can abstractly recognize the complexes, or here actually the graphs, attached to a surface inside to a subsurface inside the complex attached to the full surface. Okay, so these are theorems. Well, we are page 6 of the first paper, and there are hundreds, so you can understand that it's well, it's very sketchy. Now comes the crux of the matter, which is we're going to complete these objects. So why complete these objects? First, I should say that this is an idea of Marco Borgi. I'll talk about these things just later. I hope to give you a sort of a survey of what the historical situation is like. But now, why complete? Well, you have to complete. Why do you have to complete? for the same reason that you have to complete the pi one, the fundamental group, if you want anything having to do with arithmetic. If you want to be mean, you can say that's because algebraics don't know about the exponential function. So the exponential function is not algebraic. That's no big news. And for that reason, you do have to complete things before you can have any action, say, of the Galois group or anything which is arithmetic. So how do you complete? So if you complete a group, you get a profinite group, and you have all sorts of profinite groups. You have pro-L groups. You have groups which are a bit more sophisticated. With take a Serre class against Jean-Pierre Serre, a Serre class of finite groups, and then you get completion and so on. And here you do the same. So what you do is so you have to prove something. The thing is, if I have X, which is a simplicial complex, and a group G acting on it. Suppose G is discrete finitely generated, and for as far as we're concerned, you can think of X as being one of these complexes and G as being gamma, of course. And so G is finitely generated. The good thing about finitely generated group, there are two things. If a group is finitely generated, then it's very easy to show that characteristic subgroups or invariant subgroups are cofinal, form a cofinal sequence. And also it's a very general result that the automorphism group, then if you have G, then you can complete it. And you can also take this. And this is a profinite group. And if G is finitely generated, this is also a profinite group. This is slightly less obvious. This is by definition. This is less obvious, but this is also true. So it's nice to have finitely generated groups. So if you have a simplicial complex, say, or a simplicial set, if you're more algebraically inclined, and actually it's probably better to think in terms of simplicial sets. And the group G acts on it. It doesn't have to act simplically, that is permuting simplices, but it does have to act finitely, virtually simplicially. So the action is virtually simplicial. And also, so again, I'll denote the G by I'll denote the open subgroups, that is the finite index subgroup of G as G lambda for lambda in lambda, which is you call it a projective system. And you want X over some G lambda. So if it acts virtually simplicity, take G lambda small enough, and you want this to be finite. To be, when I say finite, I say a finite simplicial complex. And then which is, okay, both things are true for our complexes, for the complexes and for G equals gamma. So the action is virtually simplicial and the quotient is finite. And then you say, well, then you do the obvious thing. You do this. So you take the quotient of X mod gamma lambda, and you take the limit, the limit or the projective limit over lambda. And this is the completion of your simplicial complex. Maybe I should say that there's a very nice volume, this one, which is the volume of the proceedings of a conference in Kyoto 2010. So it's already 15 years ago. And in there, you can find a paper, well, you can find a paper of mine, which is very long and explains tons of stuff, including this, but also a paper by Gerjon Quick, which sets all these things up in terms of Quillen's, how do you call them, model categories. So there's this can be done in a very clean way. And this is done in a very clean way. So now we are in a different world. I mean, you should really think of what happens when you complete this and you're in a completely different world. It's like going from, of course, complex analysis to p-adic analysis, and that would be like a toy model. So, for instance, the toy model is, well, first, this is not compact usually, and this is compact, okay? So the toy model would be, think of the shift z equals to z plus 1 on z and on zp, okay, where zp are the p-adic integers. It's completely different, because on z, not much happens. I mean, you have a shift by 1, and then you go from minus infinity to plus infinity. And on zp is compact. So whenever you're close to p to the n, then you're very small. You go back to a neighborhood of 0, and zp is compact. So this is very simple. A little less simple is you cannot use anything having to do with, there's a large body of theory by Thurston and which has been developed further. When Grothendieck was writing the Esquisse d'un Programme, he said, maybe what I'm doing has to do with what Thurston is doing. And indeed, I think it's true. And I tried to explain why in this volume. Let me take one example. The first example, which fails, to show that why it's completely different. So if I take 3 curves, okay, and then I take the twist of one curve by the other curve, and then I look at the intersection points. I look at the number of intersection points, and I twist n times, which is a way of going to infinity. This goes exponentially. This increases exponentially. Of course, you have to avoid the case where alpha, beta, and gamma are disjoint, or something are disjoint, and this is 0 for obvious reasons. But in general, I mean, if you, with suitable, very simple assumptions, this increases exponentially. This is one of the first results of Thurston theory. It makes no sense in what we're doing. It makes no sense. Nothing makes sense. You will be, well, first, we don't have curves, we'll have pro-curves, it's very complicated and so on. Second, there are no intersections. You cannot count intersection points, makes no sense. Third, it's compact. So it makes no sense to say that you're going to infinity because you're not. And so the whole thing is meaningless. So you have to resort to things which are really, really different. At least I should tell you, I mean, I won't be able to tell you much, but I should tell you maybe, should I tell you what the congruence topology is? Should I? Because, you know, in our case, in fact, there, you know, if you're in this situation, you can look at alt G hat. And this is exactly what we're doing now, because gamma is essentially alt the automorphism group of the pi one. And you want to, and gamma hat is the completion of this. But you can also look at the automorphism group of G. Maps into the automorphism group of G hat, and then you can look at the closure of this. Okay, and this may or may not be equal to G hat. Sorry, G itself is, well, okay. So let me just say what happens for gamma. So you have gamma, and you have gamma, and let's do this. So gamma is so gamma k is the elements of gamma, such that gamma acts trivially on sorry, here it is. Okay, so you have an element of gamma, okay, and it's like when you form the Torelli group. You take an element of the mapping class group, it acts on the pi1 of your curve, and then you take the elements which act trivially on that, where K is some invariant subgroup. Subgroup of pi1. Okay, so what am I going to say? Yeah, gamma k is called a principal congruent subgroup. So that's the definition. Gamma k is a principal congruent subgroup. Okay. And a congruent subgroup is anything which it's a subgroup which contains a congruent, so a principal congruent subgroup. And gamma hat, or gamma check, is by definition the limit of this group. So this is a this is a subsystem of the open subgroup of gamma. Which is not so obvious. It's not like the pro-L, or it's slightly different. And it's called the congruence subgroup. Sorry, the congruence completion. So gamma hat is it's called the congruence completion. But by the definition, of course, you have an epimorphism from gamma hat to gamma check, quite simply because you've taken a subsystem of all the open subgroups. And there is a famous conjecture, Ivanov again. So the congruence conjecture is simply that they coincide, that this is an isomorphism. So why is it important? Why is it important? Because, quite simply, because the congruence conjecture, the congruence completion is much easier to manipulate than the full profinite completion. So this gives rise to C hat of S, or C Chesh, sorry, of S. No, not the conjecture. This gives rise to this completion. Just by taking the same limit only over this subsystem. So then there are many things you have to show, for instance, that they're residually finite and things like that. Why is it important? Because, and I'm not going to elaborate again, but of course in the papers it's explained, because basically what you're doing is, instead of considering the covers of the moduli stack, you're actually consider the cover of S itself, and it's much easier, of course. The cover of the surface are much easier to deal with than the covers of the moduli space. So roughly speaking, roughly speaking, but it's of course, again, it can be made quite precise. The congruence completion allows you to pass from the very complicated and mysterious covers of M of S to the much less mysterious covers of the surface itself. Because I mean, the subroof pi1, after all, is if the curve is affine, that is, if there is at least one puncture, if n is at least one, then pi1 of S is simply is free, and if not, it's a surface group. If the curve is projective, it's a surface group, but it has many properties, and it's much easier to deal with than gamma of S. Okay, so now I have to end basically this very sketchy survey with the results, the key results, which are in the second paper. Well, no, one of them is in the first and the other one is the second. So you remember that C of S, CP of S, C star of S are rigid. So we call them rigid in the sense that so out equals democracy. Let's call it rigid. I mean, many people call it rigid. Now there is a surprise that if you complete, they're not rigid. Well, it's not exactly a surprise. Well, no, the surprise is not exactly that. Of course, it's not exactly a surprise. I mean, you know that star is +1, and then VP star is much bigger. Okay, I mean, the invertible elements of ZP, many more. So it's not quite a surprise that these things are not rigid when you complete. The surprise is that they behave in a very different way. That is, let me just, well, this behaves like this. So it's quite important in terms of proving things, but okay, let me leave this aside. Leaving this aside, you have that out C of S is still Z mod P. So in that sense, CP is rigid. CP check, which you can sort of confuse with CP hat. Maybe I forgot to tell you that the congruence conjecture is true for G equals 0, 1, and 2. So okay, so for instance, if S is a sphere with marked points, there is no difference. So for the sake of thinking about it, you can slightly sloppily confuse hat and check. So this is still Z mod 2, but out of the, well, I'm okay. Let me check. Let me say S equals S0 and larger than 4 to be on the safe side. Then you have this. This is BT. So this is this justifies my being here. I mean, not really here, but being in. I mean, talking in this in this conference. This is sort of very believable. Well, I don't know how believable it is, but I mean, it's a theorem. But the outer, also, again, everything has to be proved. For instance, it's not at all obvious, not at all, that gamma hat is yeah, for instance, you have to prove that gamma hat is normal in alt d hat of s. This is difficult because otherwise alt wouldn't mean anything. So you have to prove the normality of this. So you have to prove this. Here I have hats because it's genus 0. The congruence conjecture is true for G equals 0. So I mean, you can write hat instead of check. It's not obvious at all. So you remember that it's also true that G is GT hat for n. Oh, sorry, 0 for n larger than 4. This is so you're not using this. You prove this. This implies this, and it implies actually more because of what I said about finite index subgroups. So it tells you that any finite index subgroup, for instance, if you have a, I'm not going to write it down, but it's written down in the paper. If you have a finite index normal subgroup, then you can compute out as an extension of GT by a finite group, which is essentially the Galois group of the extension. And that's because alt star equals alt in genus 0. So maybe I should have said that. This is a recent result. Gamma of S. If the genus of S is 0, and this is quite a recent result by I'm sorry, I remember Mochizuki and two other people. So it's a joint paper, and they show that I mean, Tamagawa will know it much better than I do, that you can erase its R, as we say. I mean, any automorphism will be inertia preserving. Okay, that's just it's just the flavor of what you can do. Actually, there are many results. Some of them striking, some less striking. And now I really would like to take 15 minutes to tell you more about the background, because I think the background, you know, these things have happened many years ago, in fact. What happened is, well, Grothendieck wrote his esquisse in 1984, and the esquisse is geared towards nonlinear, a foray into nonlinear wild stuff. And it's deeply pro-finite. Then, as you know, in 1990, Delin wrote his paper about P1 minus 3 points. And he said that Grothendieck had told him to look at P1 minus of the fundamental group of P1 minus 3 points which is I mean, if you take it over Q bar over C and you take the étale, and it's just it's just the profinite completion of the free group on two generators. And Delin says, well, I don't know what I can do with it, because what can I do with the profinite completion? And he said, now I'm going to deal with the pro-unipotent completion. So it could sound harmless, but actually it determines a complete turning point in what people were doing. The ironical thing is, Delin said, now I'm going to use motives, which anybody who has read Récoltes Sommeil will find especially an ironical epilogue. That's why I call this paper an ironical epilogue to Récoltes Sommeil. Of course, the paper is very interesting. Of course, people have done very interesting thing in this pro-algebraic setting, which is much better known, and more people have been using it. Now, let me try to say a few words about certain tensions, not personal, but tensions about mathematical tensions about certain things. First, it's obvious that what Grothendieck started with was the obvious remark that the fundamental group is the only non-abelian, so he called it, he eventually called it anabelian, the only non-abelian invariant in classical algebraic topology. All the other invariants, starting with the higher homotopic groups, are abelian or linear, okay? So he really wanted to have to do with pi1, which means having to do with k pi1s. Now, if you want now having to do with pro-algebraic completion is just impossible. Pro-algebraic completions are enormous. Well, actually, there's a paper by Serre in the old book, in the 1991 book about motives, where he explained that. And there is actually a paper by a theorem by Tits, a very old theorem by Tits, which also explained that. So in some sense. So algebraic completions are much too big to be dealt with. So you have to be content with pro-unipotent completions, which are much smaller. Now, of course, if you go to pro-unipotent completions, why do you go to pro-unipotent completion? Because it was the time where rational homotopy theory was being developed, and rational homotopy theory is geared towards simply connected spaces. So it's the exact opposite of what Grothendieck was trying to do, which is k-pi1 spaces, and rational homotopy theory has to do with simply connected spaces, or say at most you can accommodate a fundamental group which is nilpotent. So I mean manifolds with nilpotent fundamental groups. So in some sense, this is a weird start because you start in the exact opposite direction. You start with a theory, pro-unipotent, which is essentially linear, because you want to reduce homotopy to cohomology. And you start with things with manifolds which are supposed to be, or are supposed to be simply connected or not far from it. And whereas what Grothendieck was trying to do is to attack k-pi1s with three branches, which we know, which are Galois-Teichmu theory, which became Grothendieck-Teichmu theory, the section conjecture, and abelian geometry. So there is already that.
Yeah.
Yep.
Let me just interrupt you. So it was scheduled for 1 hour.
Yes.
And you're a little bit over the time. So.
Oh, I thought I had started at 15 minutes after.
No, I think we started just on time.
Oh, did we start on time? Yeah, oh, sorry.
No problem, but you mentioned the section conjecture, and you see there's a discussion. Just
yeah. No,
20 past 3, where you can talk again.
No. I mean, I'm sure you have a real specialist of the section conjecture, which I'm really not. Okay, let me finish in 2 minutes. That's okay? 2 minutes?
That's fine.
That's fine. Okay, so what I just want to say is maybe there are also two sides of Grothendieck-Teichmu theory. First, I mean, many sides, but there are several dichotomies, says. One is between pro-algebraic and pro-finite. So I'm advocating also the pro-finite side as being closer to what the esquisse is trying to achieve, but that may not be such a very good reason. But much more has been done that has been advertised. The second dichotomy is between genus 0 and higher genus. So genus 0 is essentially braided categories, and but not genus. Higher genus is slightly different. And there's a deeper dichotomy between, say, Gawa theory and a form of universal deformation theory. So I would insist that universal deformation theory, which is much more what I was talking about, and actually, if I had more time, I could be much more precise, and you would go to really universal deformation theory. So universal deformation theory of what? Basically, the simplest structure is associative algebras. So deformation theory of associative algebras was started in the early 60s by Murray, Guest, and Haber. And then you can say that the quantum groups and all the beautiful work of Drinfeld is also, of course, connected with that thing. So people have laid an enormous stress on the fact that grothendieck-teichmu theory was trying to approximate the Galois group in a geometric way, which is true because I mean even Grothendieck says it. But I think grothendieck-teichmu theory also has to do with a universal form of deformation theory. These two things are very difficult to reconcile. It's very difficult to understand why Galois theory on the one hand and deformation theory on the other have to do with each other, and in fact, in some sense, should coincide with each other. But okay, that's maybe I'll stop here because sorry, I misunderstood. I didn't remember at the time when I started really well. Thank you. Big silence.
Okay, did you hear the applause?
No, but
Yeah, so
it doesn't much matter, really.
Okay,